Welcome to Algebra 2. Today we've got part 2 of our section 9.1 kind of review of right triangle trig from geometry. And this deals with finding angles. So yesterday we learned how the trig ratios deal with right triangles, and everything was with regards to sine length. We always had or side length. We always had a given angle measure that we could use our trig ratios to solve. Well, what if we do if that's not the case? So we need to know how to find angles, and it's just manipulating the function to work how we want it. When we want a different result out of that function, how can we adjust it? So let's go back to take a look at what our trig functions, again functions, not ratios, how they worked. So normally, like we saw yesterday, when we are trying to find the sine, it's of an angle, and we know that angle, so we can use our calculator or something, type in the sine of 57 degrees or something like that. But we have an angle for an input, and we'll get a ratio or a decimal as an output. Well, what we're going to want now is, if we're trying to find an angle, then we want to use an inverse trig function, because we want to be able to plug in some ratio of side lengths or some given decimal, and we want to get an angle measure as an output. So we're flipping the input and output. It's just what we talked about all year an inverse function does. So that's what we're going to look at today, is an inverse. And you've probably seen these keys on the calculator that say like sine to the negative first power. Remember, negative first power is a way of saying inverse, right? Whenever we found an inverse function, we said it was f inverse of x. Another way of saying sine inverse is arc sine. And again, that's just so that we know if we're not trying to find the ratio, that we're using a different function. It's just different terminology. All right, so our first example here, we've got some mystery angle theta, and when that mystery angle gets plugged into cosine, the ratio that comes out is negative root 3 over 2. So we're going to use our inverse trig functions to get the output here in, it should say in degrees. We're still in degree mode with our calculators, but just some practice with that. So letter A, before I dive right into the calculator with this, root 3 and 2, man, that's looking like it could be coming out of a special right triangle. So I want to think there's some pieces of this that might not quite be something we've dealt with just yet, but by the end of the chapter, we'll definitely be able to answer this question very, very quickly. But let's just think, if we have some mystery angle theta, what this is saying is that the cosine, the adjacent over the hypotenuse, is root 3 over 2. And they're giving me some negative value like this. So I am going to turn to the calculator for this. But just so we know, like root 3 and 2, man, it sure looks like that should be a 1, right? And we've got some 30, 60, 90 right triangle going on. So definitely realize that by the time we get to the end of this chapter, we'll be able to answer this very, very accurately. But for now, we're going to stick to using the inverse in our calculator. So I'm going to type in cosine inverse, because I want that angle as an output. Let me just write this down so we can see if I'm using the inverse function, then the ratio goes in and the angle comes out. So cosine inverse negative root 3 over 2. Being very careful with parentheses there, and I get 150 degrees. Exactly. Okay, and I'll leave it to you to kind of wonder why an angle of 150 degrees is leading us to a 30, 60, 90 right triangle. That's a good kind of guiding question to kind of, I don't know, make you a little bit curious. Okay, for letter B, here we're given a decimal, right to the calculator here. So let's see. We want sine inverse of negative 0.7071. And I get, well, it rounds to negative 45. Well, how can an angle measure be negative? The calculator's not lying to you. Well, we've just seen some really weird things. We saw a ratio that looks like it's coming out of a 30, 60, 90. and we got an angle of 150. Now we type in some trig ratio and we come up with something negative. Oh, this is weird, weird, weird. But again, we're going to cover this in a couple sections, so be patient. These questions will be answered, or go look it up and kind of investigate it on your own. This is all perfectly fine. And lastly, letter C, tangent theta. Wow, this looks suspicious. Root 3 over 3, after doing all of that rationalizing the denominator work, this looks like a 1 over root 3 to me. And I'm seeing 1s and root 3s. Man, I'm thinking again that if I had some special right triangle, this certainly looks like a 30, 60, 90. I've got an opposite of 1, an adjacent of root 3. Man, I would expect that hypotenuse to be 2. And that sure looks like if this angle's opening up to the shorter leg, that has to be 30 degrees. Now, I'm going to box it up now, but I want to confirm with the calculator first. So let's see, tangent inverse of square root 3. I'm going to type it in just like I saw it, divided by 3. Hey, and it's exactly 30 degrees. So I just get this idea of we're looking for an angle that creates these types of ratios. And yes, we can get angles that are not acute. Yes, we can get angles that are negative. We just don't know why yet. Totally acceptable outputs, though. Okay, here's one of our big tasks. So taking this concept, and here's probably how you remember it from geometry. We have a right triangle, and all we know are side lengths. So how can we find the indicated angle measure? Well, if we're finding an angle, we want that as an output, we need to use inverse trig. I'm still going to look from, I want to establish what angle I'm looking from. That's going to help me decide, is it opposite or is it adjacent? So in the case of letter A, my opposite side is 8, and my adjacent side is 14.9. That means I'm going to use opposite and adjacent. That uses the tangent function. So the tangent of my unknown angle is 8 over 14.9. That means if I flip input and output, tangent inverse of that 8 over 14.9, that'll give me theta. So let's type that in and see what we get. Tangent inverse 8 divided by 14.9, and I get 28.23. Okay, this is an angle, and it is measured in degrees. So I round it to the nearest hundredth of a degree. Now, these triangles are not in any way drawn to scale, so don't think that, oh, that looks like it's about 30 degrees, so I'm going to put some, hopefully I get something close to 30 degrees. That happened to work here, but it's not going to work every single time. I can tell you what, I just copied and pasted. So not to scale at all. Letter B, from this angle, I've got my opposite side and my hypotenuse given. That means the sine of that angle is the ratio of opposite over hypotenuse. And if I'm trying to find the angle, I want that angle as an output. I want sine inverse of that ratio to get that theta to come out. To the calculator we go. Sine inverse 3.7 divided by 9.2. And I get 23.71 degrees. Now, we haven't learned about these yet, but if you just had the answer 23.71, you would not believe how wrong you are. We're going to learn about a different type of measuring angles called radians coming up in, well, maybe even just next section, I'm not sure. But it comes up pretty quickly. So if it is a degree measure, it has to have a degree symbol on it. We have to have that. Otherwise, it's assuming that we're in that radian mode. All right, so example 3. Now it says solve the triangle. And we've got a couple different cases. You can see letter A, we're given an angle measure. However, in letter B, we are not. So if we are given an angle measure, then we're in really, really, really good shape. Because what do I need to find? Well, I need to find the measure of angle B. So the measure of angle B, wow, it's been a while since we've seen that type of language, huh? The measure of angle B, if I'm given one of the angles, finding that other angle is not going to be difficult whatsoever. I know all the angles have to add up to 180, so I can just do 180 minus the 90-degree angle happening at C minus 62.5, and I just come up with 27.5 degrees. Okay, I'm going to go ahead and label that in the triangle as well. Hopefully we've been pretty well coached in geometry with that. Now, I want to avoid using any rounded numbers that I come across, so I like to always refer back to my given information. So to find another value on this triangle, I'm going to go for AC. So from this given angle A, I didn't round that, I didn't touch that at all. 12.2 is my opposite side, and I want to find the adjacent side. All right. So let's see, this would be side B because it's across from angle B. To find side length B, then, I know that opposite and adjacent, hey, that uses tangent. So the tangent of that 62.5 degree angle that I know equals the opposite side 12.2 over the adjacent side B. B is going to equal 12.2 over that tangent. And we'll turn to the calculator. And I get 6.35. Label the diagram as well. Okay, and lastly, we need to find the hypotenuse, or side length C, up here. And I've got a couple different options. I could use that 62.5 and use maybe, and this is what I would choose because I think it's fastest. I would use, again, I've got 12.2 as my opposite side, and I'm trying to find the hypotenuse. So I would say, okay, well, the sine of that 62.5 is going to equal 12.2 over the hypotenuse. A little bit of algebra. I'd have to multiply over the variable c and divide away the sine 62.5, and I'd turn to the calculator again. And I get 13.75. Another way of doing that would be to use the Pythagorean theorem. Once we found the 6.35, we knew two of the legs of that triangle, that we could use Pythagorean theorem. We would get the same answer. However, if I was using Pythagorean theorem, then I would have used a rounded value. That 6.35, I rounded that, so my answer for hypotenuse may be off by a little bit since I used a rounded value. Plus, I think the trig is so much faster. Once you have it set up, you can go immediately to the calculator. You don't have to type in as much. You don't have to use that huge square root or anything like that. Less chances for error, I think. The other situation here, letter B, you can see we are given two of the side lengths. Well, it'd be really easy for me to solve for the side length A over here just using Pythagorean theorem, and I'll do just that. I'm not using any rounded values. So to find that side length A, I would take the square root of my hypotenuse squared minus that one leg squared. So let's see what the calculator says for that. Square root of 7.6 squared minus 3.9 squared. And I get 6.52. And just for sake of space, I'm going to label these right on the diagram. Now I know all three sides. I just need to find one angle, and it really doesn't matter which one I choose as long as I remember to use the given measures, not that rounded 6.52. So if I'm looking from angle B saying, hey, I want to find that, I've got the opposite side given and the hypotenuse. So that uses sine. The sine of angle B is going to equal that 3.9 over 7.6. If I'm trying to find the angle, I better use the inverse. I want that angle to be an output. So I'll type that in. sine inverse of 3.9 divided by 7.6, and I get 30.87 degrees. Okay, and I know that all the angles in a triangle have to add up to 180. So I can do 180 minus 90 minus 30.87, and I get 59.13 degrees. So the measure of angle A right here, 59.13 degrees. A really, really neat idea of these trigonometric functions tying in with some of the geometry that we've done with right triangles and just coming together to solve a problem. And I mean, right triangles, this is how people measure distances where they can't cross a river or something like that. This is how surveyors, if you've ever seen, driving along the interstate, people have like these tripods and they're looking through these little viewfinders and stuff. They're measuring angles to help them calculate, a long, long distance. How much asphalt do we need to cover the road if I'm going to span from here to there? I don't want to run a tape measure that long or anything like that. So I'm going to use trigonometry to do it very, very accurately. Really cool stuff. Our final example. From a lighthouse, you spot a ship 2 miles offshore. You know the lighthouse is 475 feet tall. What is the angle of depression from your spot atop the lighthouse to the ship? All right, so we've got our lighthouse here, and I apologize, it's kind of a crude drawing. It is 475 feet tall, and it's on the coastline. And then way out in the ocean, we've got this ship right here, okay, and we know that the ship is 2 miles offshore. So that's 2 miles, but since my lighthouse was measured in feet, 5,280, that's 10,560 feet. So we're going to want to use that label to measure over to the ship. Now, angle of depression. This is a vocab word that we may not be familiar with. If we're standing up here on top of this lighthouse, if we were looking out perfectly horizontal, and then we turned our line of sight down to look directly at this ship, what would that angle be? So this one involves a little bit more geometry, actually. Pretty cool how it works. We can definitely see the right triangle forming, but the problem is the angle that I'm trying to find is outside the triangle. So what we need is the notion that these are parallel, right? They're both perfectly horizontal, and this angle right here, theta, is the same as this alternate interior angle that's happening down at the base of the ship, or where the ship meets the water. Now I've got this angle that I'm trying to find, and from that angle that we've now filled in, we have the opposite side and the adjacent side. So that means the tangent of that angle is 475 over 10,560, and our units are both in feet, so the ratio is good. But I want the theta, so I'm going to use tangent inverse to get that angle as an output. 475 over 10,560. That will give me theta. Let's figure out how many degrees we're looking down. Tangent inverse 475 divided by 10,560. And I get 2.58. Which, if you think about a protractor, 2.58 degrees, you're not looking down very far. But that makes sense because that ship is so far away. If you're looking straight out, you don't have to look down very far to find that ship on the horizon. All right, so there we had a nice little review of using inverse trig functions. Hopefully that was a pretty pretty nice refresher and not too intimidating or anything like that. Your assignment for this section is just going to be a worksheet. The textbook does not include using inverse trig functions, but it definitely does play into what we're trying to do here very, very nicely. So I feel like we definitely needed to add this in to bolster our understanding. That does it for the second day here on 9.1 in Algebra 2.